tedious after a time, and but I at least got started on most of them. The first one is hopefully letter A, and like I said, if you did the other version just from the book, you're going to have a different set. But hopefully you recognize this as being integration by parts. Integration by parts, by the way, is anytime you have two different types of functions multiplied together. Think of parts as being the reverse of the product rule. So integration by parts, you have a product, you're like, I got to disentangle this product. And here, I thought about it before. I almost wrote down u equals 4x cubed, but then I hesitated because I realized that using u equals 4x cubed, I'm going to have to do this at least 3 times, because you're going to have 12x squared for your first derivative, and then you're going to have to do it again and have 24x and then 24. So to sort of shortcut make this a little quicker, I made this table, and hopefully you remember me doing this earlier. And this is just to help me to do integration by parts multiple times in one fell swoop. And so just to remind you how you use the table, we have your u, your dv, and then you just do derivatives until you get to 0, and do integrals. These are all the you do the integrals until you get to the same level down there. I guess I'm going to have to go fix some of these back here. I was rushing this morning, let's just say. Okay, and then you do these diagonals because, as you know, you always are going to have u times v, and then you do the integral of v du. So it's always u times v. If this is dv, then this is v. So u times v, and then this is u times v. This will be u times v. This is u times v. So if you've got that all sorted out, then let me just make sure. So this one, it's the first one is positive, then the next one is negative, then positive, then negative, because u times v minus the integral of v du. But then you have u times v minus double negative, because you've already minused here. So that's why it's plus minus plus minus. Let me go fix my pluses and my minuses over here. So let's see, the first one is positive. That one's, now that's correct. Second one should be negative, but it's minus a negative, so it's positive. Then the third one down is plus a negative. So I need to fix that. So, whoops, sorry. Here we go. And then the last one is negative minus, and yeah, that's all correct now. So there it is. Like I said, you could have done this using integration by parts 3 times, but it just is a lot more writing. Look how quick, short this is. Okay, so there's A. Let's see, maybe we should get all of the integrations by parts. This one, G, I just left that one out because it was so easy. I thought I'll just do this one in front of you. That's an integration by parts as well. So remember, what I'm looking for, integration by parts, is when you have two very different functions that are multiplied together. In this case, though, instead of letting u equal 5x squared, I'm going to let u equal the natural log. And the reason for that is that I want to make things simpler when I do my integration by parts. And if u is equal to natural log, the derivative of natural log is 1 over x. So that's going to be way simpler if I do it that way. So let's actually do that. du is equal to, well, using the chain rule, 1 over 3x times the derivative of 3x, which is 3. So you do get 1 over x. V here, times dx. And v here is going to be 5/3 x cubed. So let me just pause there. This, by the way, is letter G, in case you weren't paying attention. And if you didn't have the worksheet, once again, I apologize. It's on Moodle somewhere, but just dig it out of the... Okay, now we're going to write this down. And I think I encouraged you to do it like this every time, is to write it out to help you remember. I have written this down like this hundreds of times, maybe thousands of times in my life. And so I have this firmly embedded in my brain, but you might not. And that's why I suggest always write it down when you're using integration by parts, just to remind you, here's the form. This is what we're doing. So let's go ahead and do this. So let's see, u times v is going to be natural log of 3x times 5/3 x cubed, and then subtract off the integral of v times du. And notice that I've canceled the 3's. That's fine. So we got this. And then the next level is so easy. I almost, well, I'll do it, but 5/3 x cubed ln of 3x minus, let's see, this is going to be, can I do this without writing another step? Let me just speak it. This will be 5/3 x squared. So you can do that antiderivative. You'll get 5/9 x cubed. So yeah, when you have two things that can be combined, combine them. The integration by parts is only useful when you have two things that are different types of functions like this. You have, especially when you have a polynomial times a transcendental function, like e to the x or sine of x or natural log of x. So anytime you have that, integration by parts is really handy. All right, that look good? Hopefully I got that one right. Like I said, I did that one on the fly here. There's one more, at least one more integration by parts, and I think I skipped it as well, thinking that we would talk about it. Yeah, yeah, you see, I put an equal there, and I was like, oh, I don't want to do this. So this is, yeah, we probably should do it. Actually, when I wrote that equal there, I was actually trying to do it all in my head. I thought maybe I can just write down the answer. I know the answer is going to be something like 1/5 times e to the x times the quantity of like sine of 2x plus 4 sine of, or cosine of 2x, something like that. I don't know. I don't know if my numbers are probably wrong, but so that's what happened there. So let's actually set this one up, show you how this works. And then, yeah, this one's kind of fun. And then we'll get on to the other types of problems. So we have u is equal to sine of 2x, if that's all right. Just because I don't want to have fractions if I can help it. dv is equal to e to the x dx. So v is equal to e to the x. du is 2 cosine of 2x. So if you chose the other way of doing this, it's totally fine. Nothing wrong with it. It just, you'll get the same answer. It's just that it'll be more work because there'll be extra fractions, and I'm trying to avoid those fractions. Okay, so here we are. Let me just go grab my integration by parts. We're going to be using this twice. Copy. So 2 times we're going to have to do this. Not to worry, it's not going to be that hard. So here's the form. So let's write it out. This becomes equal to u times v. So sine of 2x times e to the x minus the integral of 2 cosine of 2x e to the x dx. There we go. Okay, we're going to just do it again. And I think I mentioned that if you do integration by parts more than once, always stick with the same stuff in terms of your u and your v. So now my u is cosine of 2x. My dv is e to the x dx. I know there's a 2 there. We'll deal with the 2, don't worry. Du is the negative sine, 2 times sine. And v is e to the x. So we're going to do this again. There it is. All right, let's see if I can keep all of my bookkeeping. Let's see, sine of 2x, e to the x. Here's the 2 that I promised. So that 2 there I've just got right here. Okay, let's do u times v. So I have u e times v minus the integral of v du minus 2 sine. Let me clean things up just a bit, and then we'll see why this is so amazing. I know we did one of these earlier. I love these. These are just so much fun. No, not plus, minus 4 sine 2x e to the x. There we go. I think I've got everything accounted for. Let me double check my negatives. That's what makes me a little worried, is I've got negative 2 times this. That's good. So you remember I spoke the answer just a little bit ago. I was off. I think I said plus here instead of minus, but that's, anyway. And then here we have negative times triple negative, which makes that negative. Ignore this. That's the answer to the next one. Let's get rid of it. Go down here. Okay, so now the thing that's so incredibly beautiful about this is that on the left of this equation, I have up at the top, I have the integral of e to the x sine of 2x. And on the right, I have 4 times e to the x sine of 2x, the integral of e to the x sine of 2x. So there's 1 of them over there. There's 4 of them over here. Let's just move this integral over there where it belongs. I guess I can copy this. Just a minute. Here we go. Copy and paste. Put it down here. Okay, so these 4, I'm going to just delete them. And I'm going to put a 5 out here. So over there, so you have 4 of these integrals on the right, 1 of them on the left. I'm going to move the 4 over to the left, and you end up with 5 of them on the left. And so that's why the final answer, just divide everything by 5, and you get the answer. So I was close. When I just said the answer, I was just off. I had a plus here instead of a minus. So very nice. And by the way, if you did the opposite, you would have, it's going to look a little uglier, but you could simplify it to turn it into this. I think you'd have a bunch of fifths and fourths. But that was fun. I don't know. These I love all of these. It's so much fun. But this especially, when you can kind of come at something around, like you get the answer without actually getting the answer. I love it. Okay, so let's move on. Any other questions about integration by parts? So remember, this is one of the things that we're doing for this section that we're kind of skipping now, is whenever you have a product of 2 things, that's a clue that you're probably going to use integration by parts. Okay, the next thing, what other clues can we see? Let's see, where am I on my list here? I don't want to do B yet. I don't want to do C yet. Okay, how about this one? So there. I know I just did it in my head. Like, how'd you do that? Okay, so here's the next thing. Now, you might look at this and say, that looks like a product, and I think you probably could get away with using integration by parts. Here, let me show you the product. The product is this. You have natural log of x times 1 over x. So I think that you might be able to get, no. No, you're going to have a problem if you try to use, well, I don't know. I've never tried this. Whenever I do this, I don't use integration by parts, but you might be able to use integration by parts here. I don't know. So if you did and it worked, good job. Here's what I did though, is the second thing, so first thing, is there a product that I can exploit using integration by parts? If there's a product, use integration by parts. Second thing that I look for is, can I use substitution? Now, that might be your first move, which is fine. Substitution is the reverse of the chain rule. So here you can use substitution. How do you know? Well, here's what I look for. I look for a function and its derivative. So if both of those things are part of my integral, then I can use integration. I might be able to use integration by substitution. What's the function and what's the derivative here? Does anyone see it? Yeah, what do you think, Hayden? Yeah. No, you had it right. You had it right. Function is ln of x. Let me write it down. So I'll write it down as a substitution. So you have u is equal to ln of x, and it's exactly what you suggested, that the derivative is 1 over x. It almost is too easy now, isn't it? You can see exactly why that's the answer up there, but let's go through the motions. So you have u squared du, or no, I got ahead of myself. There, u du, and then you just do the antiderivative of u, which is super easy. U squared over 2 plus c, and that, when I do put the substitution back in, I get that. So you're looking for a function and its derivative, and that's how at least clues us into the idea of using integration by substitution. By the way, all of those trig integrals, that's what you're doing, is you're trying to set up a situation where you have a function and its derivative. And let's take a look at this one, which once again, I just did it in my head, but you might have needed a little bit more time to do this or room. So here, the function and its derivative. So you could go either way with this, I suppose, but the way that well, actually, it would be hard to go the other way, but here's the way I'm doing this, is u is equal to sine of x, and the derivative of u is the cosine of x. So anytime you find a situation where there is a function, sine of x, and its derivative, cosine of x, that are lying around, you probably can exploit that to do integration by parts. Here, let me just move this again. Keep moving that. Here. Just so that we can see this. So, and I know I've beat this, probably this is a dead horse, but I always, and I know that this isn't something that you do because I've seen your work, but it is so much better if you just take the time, it doesn't take that much time, to rearrange your function so that this du is all by itself. That way you can be sure that you've got it right. And I realize that probably some of you were taught Calculus 1 by teachers who told you shortcuts, like just divide by 2, or don't worry about it, it'll all come out in the wash. I'm worried. So I'm going to do this, and you should be worried too. So let's go ahead and finish this up. Now that you've got it like this, it's easy to see that this is going to be the integral of u squared du, and of course that's u cubed over 3 plus c, and that's where that came from. So I hope none of you had trouble with j, but there it is. So there's j for you. I don't remember if there were any other substitutions. Let me see. Oh, I guess there's this one. Yeah, this one. Oh, look, I didn't finish it. But here, so this is one of those dreaded trig integrals. But if you just think of it in terms of a function and its derivative, this is kind of the way you're going to set this up. You have the function secant of x. I guess I got excited and put theta in there. And you have tangent, secant times tangent of x, and that clues us in to how we're going to rearrange and I know where you are in your stage of development. I was there once. I would try to write as little as possible. There's no way I'm confident that my papers back when I was taking Calc 2 did not look like this. I was not fastidious. I was not careful. I got problems wrong on tests as a result. I'm just trying to help you out, trying to keep you from getting those problems wrong. So I've got my du. Look at that. Du is right there in parentheses. Everything else is correct, isn't it? I'm going to do actually two more steps. No, one more step before I do my substitution. And that is tangent squared is secant squared minus 1. So secant squared minus 1 is tangent squared. And I try my best to, when I see you skip these steps on your tests, to extend the grace that you deserve. But if you get it wrong, it's harder for me to award partial credit. That's another thing. The more steps you show me on your exam, the more I can identify what you did wrong. And if it's something like you might have put a 1 in instead of a 2 or left a negative out, I'm usually pretty gracious about that. I'm like, I'll just take off a point. But if you don't know your calculus, that's when I start taking off big chunks of points. So show me your work. The more you write, the better for you. It gives me a chance, if you get it wrong, to say, oh, it was just something stupid. You didn't get enough sleep. You played too much Need for Speed last night or whatever it was. Okay, so let's actually, let's finish this up. This is going to be u squared minus 1 times u squared times du. Almost too easy. U to the 5th over 5 minus u cubed over 3. Okay, I did skip a step there, but I think you can handle it. So this is going to be secant to the 5th over 5 minus secant to the 3rd of x, whatever, over 3. So there's your answer for that one. All right, any questions about any of the substitutions, including the trig substitutions? I'm saving the best for last. I know you're looking forward to these last few. But was that one okay there? Any other issues? Okay, so the last few, we have a couple of trig substitutions and then partial fractions. And I think that'll round it out. Let's talk about partial fractions first, because that one is much easier, honestly. So the partial fractions, I don't even show my work with this one, but you can, hopefully you got the same. I'll show the work now. So here's the partial fractions. You have 1 over x squared minus 3x is equal to a over x minus 3 plus b over x. And I believe that you get a equals 1/3 and b is negative 1/3 as the answers to that one. So I know it's still not showing a lot of work, but this is what I did to get those. I actually just, did it. These are easy fractions. So you get those, you put this, I factored out the 1/3 because the fractions annoy me, and you get this. And then by the way, this is completely acceptable, this up here. I just did this because I thought it would look cool. So. I know, it's the best. Okay, so anything with the partial fractions, we're happy with that? Okay, these last two. I was just typing these up and I thought, oh, we need a couple of examples of trig substitution. And man, these are so ugly. What I want to do, I will show you the starting part, and then things got really ugly. And then I went to Python and I did it in Python. So I'll show you. I just gave up. I'm just being honest. Okay, so anyway, but this is the important part, so that we've got the important part here. So you've got your triangle. You want to set it up so that it works with the Pythagorean theorem, and you want this radical to be on one of the sides. Turns out that because there's a plus, that radical has to be on the hypotenuse. And I'm going to put my x here and my 2 here so that the tangent can be x over 2. So that gave me these substitutions. x is 2 times tangent. Tangent is x over 2. The radical, which I was too lazy to even write, is 2 times secant. And then the derivative of tangent is secant squared, so dx is 2 secant squared. That gave me what's down here. So let me explain, because this is the crucial step. So I replaced x here with tangent, 2 times tangent, and I got 4 tangent squared. You see the tangent squared. I replaced this with 2 times secant. You see one of the secant, or the secant is embedded in here, and I put the 2 with the 4 out front, and the dx became 2 secant squared. That's why there's cubed here, because you have one of the secants from here, 2 of them from dx, gives you 3 secants, and this became 16. Specifically, you got 2 2's here, another 2 here, and a final 2 there. So there's 4 2's, 2 to the 4th, 16. And at this point, I just wanted to cry. Because what am I supposed to do with that? What am I supposed to do with that? I know how to deal with this if there's an even number of secants. If there's an even number of secants, I can separate out one of the secants, and I'm good because all the rest of them turn into tangents. I'm also good if there's an odd number of tangents, because if there's an odd number of tangents, I pull one of them out along with one of the secants, turn the rest of the tangents, which there will be an even number, into secants, and I'm good. But when there's an even number of tangents and an odd number of secants, all bets are off, and you're just stuck. The techniques that you could use, just so you know, is we could turn those tangents here. I'll do that right now so you can see what this looks like. I could do this. Sorry. Secant to the 5th minus secant to the 3rd. So you might wonder, what did I just do there? Well, I took the tangents and I turned them into secants. In particular, tangent squared is secant squared minus 1. Lump that in with that secant cubed and you get this. But now we're stuck again because that's not a very nice thing to deal with. So in particular, what you would do at this point is you would separate this into 2 separate integrals, deal with them individually, probably use integration by parts. Yeah, maybe there would be some weird trig stuff. So that's one option. The other option is the one that I chose, which would work, but I gave up. Just so you know, I'm just being honest with you. So here's the other option, is tangent. Tangent is sine over cosine. Secant is 1 over cosine. And so this mess turns into this mess. And then I have an odd number of cosines, so I pull one out, and that leaves me with cosine to the 6th in the denominator, which is 1 minus sine squared to the 3rd. Well, I was like, well, let's keep going, and you get this. And that's where I gave up, because I was like, I'm not going to deal with that. Partial fractions, ugh. Bad enough that we've done it. So let me show you my Python just so that you can see that I actually finally did it, sort of, even though I cheated. So here it is. Wait, this is the, what's wrong? yeah, well, you wouldn't be able to do this on an exam. So let's see, was this a minus? Just a minute, where's the original? Oh, it's a plus. Okay, so it's 4 plus x squared. Oh yeah, there it is. So there's the answer down there. If you're curious, let me zoom in so you can see better. Oh, by the way, I'm using SymPy. Just so you know, if you're into Python, great package. Lets you do all kinds of symbolic calculations. But anyway, so there it is. Just as a quick explanation, you probably recognize a lot of this stuff as being the stuff that you started out with. The only thing that you don't recognize is this arc hyperbolic sine, which you wouldn't have gotten that if you had done this yourself. The arc hyperbolic sine is actually a natural log, because the hyperbolic sine is an exponential function. It's just shorthand for e to the x minus e to the negative x over 2. So our arc hyperbolic sign is kind of like the undoing of that. So it's going to be a logarithm. So you can understand why you might get that when you're doing partial fractions. But yeah, it's just so ugly. So yeah, you would never get yours to look exactly like this, but you would probably get most of that if you persevered. Okay, so one more and then we get to move on. Fortunately, today isn't too hard of a day in terms of the lesson. So the last thing, so bear with me for this last item, is this one. When I got to this one, I knew what was coming because I had already done that much of where was it? Of letter B. So I'd already gotten to there on letter B, and so I knew what was coming with this, and all I did was I drew the triangle, and then I gave up. So, but just so you know, this triangle, you would have sine of theta is x over 2, cosine of theta is the radical over 2. This one I don't think would have been quite as bad, but I'd already felt bad about the first one. So let's just change this to a minus and see what we get so that it matches the problem. So there it goes, crank it through. Oh, I know, it looks scary. No, it's not as bad as it looks. So, because SymPy is being very inclusive about the numbers you're allowed to plug in. You see, if you plug a number into the radical, the square root of 4 minus x squared, that is bigger than 2 or less than negative 2, this would be the square root of a negative number, and so things would look different. But we're going to ignore that because we're in the real world, right? So this is the only thing. So you see a lot of stuff that you recognize, and at least this arc sine, that's somewhat familiar. And so you can imagine where that probably came from. Probably what happened was in my answer, I had something like this is equal to a bunch of stuff, and then you had a theta at the end. So there was a theta at the end, and then when you did your conversion back to x, you know that sine of theta is equal to x over 2, which means that theta is the arc sine of x over 2. So that's where that arc sine came from in the Python, if you're curious. So that's it. Wow, so much work. You know what? Oh, wait, we didn't even do this one. That one was super easy, though. Here, let me just show you in case you're curious. Why is it so easy? It's because this is this. There. Do it in your head. Okay, so if you did, I had said to at least one person before class that if you did the other problem set that I would be happy to take those questions. I've changed my mind. If you did the other problem set, I will take those questions, but you'll have to bug me later because we do need to talk about this briefly. Oh, you guys have to leave? Let's talk about this on Monday. That'll give us the weekend to rest. So this is great. Yeah, we all have to go to chapel today because the musical groups are performing, and we need to go support them. So we'll take the extra time. If you do want to talk about the other homework, the one that was in the book, like Ben did, I'm happy to do that now. Otherwise, we're all done. We're going to end a little early so we can all get good seats to go see you guys. Yes? Which homework? No. Just the yeah. Oh, stick around if you're having trouble with your uploading of homework. Yeah, you guys are all dismissed. But if you're having trouble uploading homework, let's deal with that now so that next week we'll all be consistent. And yeah, for today's homework, it should just be that worksheet. Just upload that unless you're like Ben did the wrong one. So